Hello, I'm Dr. Ron England. This is EGN3443, Probability and Statistics for Engineers, and today we're going to talk about sampling, hypothesis testing, in this case in single samples. And what I mean by single samples is you take a single sample. And when you take a single sample, you still want to compare it against something. You might want to compare the mean against a projected mean or a claimed mean, or you might want to do the same thing with the variance, or you might want to do it with a proportion. Well, let's talk about those. This is the real world stuff. Hypothesis testing is testing a hypothesis. So let's first talk about the hypothesis. Okay, the first thing is the null hypothesis. The null hypothesis is no effect, no difference. You don't differ from the known. That's it. And it's called that because it's null. Okay. Think of it this way. If you're doing statistics, you must prove it. Okay. If the sample mean or the population mean is 10 and you're going to claim it's different from 10, okay, you need to prove it. The null hypothesis is that it's 10. And it's what you said it was. The alternative hypothesis is that it's not 10. It differs from 10 by some significance level. There's your third thing, okay? But the significance level is really just the probability of a type 1 error. And a type 1 error is just the probability of rejecting a true null hypothesis. I got a new hypothesis, it's correct, and I reject it. Now, another statistic that's handy here is the p-value, which is the probability of obtaining results at least as extreme as observed, assuming, now I'm not saying stating, but I'm saying assuming that the null hypothesis is true. So if the null hypothesis is true, if it is correct, the probability of obtaining results at least as extreme as observed would be your p-value. However, if the null hypothesis is not correct, don't worry about it. Don't worry about it. So you saw those numbers. Let's go back to those numbers again. Let's really look about the ones that you're going to think about. Null hypothesis. Think null. No. Got to prove it's true. The null hypothesis is that what you're trying to prove does not true. All right, so now let's go down here to look at what we might do with hypothesis testing. And we got 3 kinds of tests, and we got 3 kinds of things that we measure typically in hypothesis testing: means, proportions, and variances. And we got 3 tests: t, z, and chi-squared. Now, chi-squared is only used really for the variance, and the t and the z can be used for means or proportions. So you kind of have to think about, when do you use the t and when do you use the z? And what I'm saying is that if you're going to compare means or you're going to compare proportions, and comparing proportions looks a lot like comparing means. I mean, it just looks like it because you got the numbers that are like a percentage or a number. Well, chi-squared, I mean, variance is a number, so I guess it's a kind of ridiculous statement. But let's just do some examples, make it a little easier here. All right, z-test. Z-test, you're going to use it when you got these conditions. One of the tests is that the population standard deviation is known and the sample size is big. So you know the standard deviation of the population, which by the way also means that you know the variance of the population, and the sample size is larger than 30. Okay, roughly 30. You always say about 30. Okay, that's one of the conditions. Or the population is normally distributed, and you know that. So the formula is relatively straightforward. You're just going to take the differences in the sample mean and the hypothesized mean, and you're going to divide by the population standard deviation divided by the sample size. So the parameters are relatively straightforward. And you use it if you know the known variant, if you get known variances, or if the real time that you use it is when you've got a sample mean that you want to see if it differs from a known mean. And in practicality, you're looking to see if a test result is valid. In other words, does the test actually, now remember, in the case of knowing a known mean, and you get a test result is probably not going to be equal to the mean, okay, well, is it still a valid test result? Or should you reject it in that case? Going with what you know, in the case of you know the population and you got a sample, you can look to see, is this sample representative of the population? Those are the things that you're saying when you do these tests. Okay, so easy to see with an example. So here's a good one. Manufacturing company claims that its parts produce parts with a mean diameter of 10 centimeters. Okay, now we're going to take a sample. 40 parts, mean diameter of 9.8, known population standard deviation of 0.2. Yeah, I think we got all the pieces that we need for doing a z-test here. It's got a lot. It's got 40 samples greater than 30. You've got a claim. The claim is that the mean diameter is 10. That's the manufacturing company's claim. I don't believe that. It may be. I took a sample because I want to prove it. Okay, I've got all the things I need for a z-test and a hypothesis. Okay, so is it 10? Is the claim correct? I am skeptical. Be skeptical. I have 40 parts that I've measured at 9.8 and a standard deviation of 0.2, and I'm going to test this with an alpha of 0.05, so 95% confidence interval. My null hypothesis mean is 10. Okay, I can easily calculate the test statistic. I've got all the numbers. Okay, comes out 6.32. Okay, got that, 6.32, and 0.05, the critical value is 1.96. And we did that in the last chapter, so I'm not going to cover that again because it just gets really long if I do that. The z is greater than, okay, the value is greater than the critical value. I reject your hypothesis. Okay. I believe that the mean diameter is not 10. Now, in this case, I did it. I just went two-tailed because 9.8 being lower than the 10 is on that other side of the tail, but it could have just easily been on the other side. So wait, you know what I'm going to do? I'm going to give you some visualizations, which I did right here. All right, normal distribution. There's your z-scores. Okay. I kind of tried to plot it right around 2. As you can see right here, those little yellow lines are. But there it is. And the rejection region is everything to the sides. Okay, but look at my test statistic. It is way over there to the left. It is way into that rejection region. You are rejecting this null hypothesis. Okay, all right. That's pretty straightforward. Now, as you get a feel for these, you can actually go back and look at those numbers and say, I'm pretty sure we're going to reject this one. Why? Because standard deviation was kind of low. And if they're all nicely, tightly bundled and you're saying it's a little bit off, well, that should tell you all you need to know. How does it say that? You should think about this. If the mean is 10, that's the 10, and the standard deviation that you measured of those samples is 0.2 with a 9.8, okay, it's kind of low. All right, let's go to the next one. Okay, we've looked at this, okay? And you can calculate all these pieces. These are all just plug and chug into the equations. I'm really looking at the concept here. T-test, okay? You saw the z-test, okay? We had a big sample, the knowns with an So now we're gonna have a totally different situation with the t-test. Well, not totally different situation because it look kind of the same, but we're gonna have a lower number. A lower number of samples is typically what you're going to see for doing a t-test. So population standard deviation not being known is one of the things. That's an unknown of the population. Okay, and the sample is the only thing you got a standard deviation from. But you're really looking at it, the sample size is relatively small. The t-test is the way to go. And the equation looks pretty much the same though. You look at the difference in the means, standard deviation divided by square root of n. and S is the sample standard deviation. And there's places that you're going to do this, but you again, I'm not going to worry about that right this minute. Let's go to an example. Easier to see. All right, now here's an example. A researcher wants to test if a new study technique improves test scores. All right, right there, I'm going to read this slowly because, okay, so we're going to see if a new technique improves test scores. Okay, we need to get some test scores then. We need to actually get a sample here. Average score of 15 students is 78 with a standard deviation of 6. Well, that seems like a kind of high standard deviation, 78. The hypothesized population mean, though, is 75. So we're really kind of looking to see the 78 is bigger than the 75. So his sample kind of makes it look like it might be. But we don't know for yet until we test it. Well, it's only got 15 students. I've only got the standard deviation of the actual scores of the students. And we've got an alpha of 0.05, so we're looking at 95%. All right, so we got the equation, plug chug, and formulate the null hypothesis. Okay. In this case, the hypothesized population mean, well, it tells you right there, the hypothesized population mean is 75. Okay, well, that's got to be the null hypothesis that the mean is 75. But in this case, the greater than 75 is that the new technique, because the new technique, if it's greater than 75, okay, then the new technique must improve scores. So let's see if that mean score is actually, and you can kind of see that sample was higher than 75, but was it high enough? Was there enough proof? All right, so calculate the test statistic. In this case, we're going to do T. It's 15. It's a one-tailed test because we're only looking to see if it's higher. So we don't care about lower. Degrees of freedom is how many samples we got? 15. So degrees of freedom is 14 because that's what you plug. Well, that's how you get the alpha. The alpha with degree of freedom 14 is going to give you the critical value, 1.76. That T came out to what? 1.94. 1.94 is greater than 1.76. We reject the null hypothesis in this case. So there is some evidence that it actually improves the scores in this one. Now, you're going to do this over and over again until you kind of get this. It just takes a little bit of time. It's not that terrible, but as you do it, you're going to do it. You'll get it. Okay. That was that sample. I did not make a visualization of that sample. I could have easily made a visualization of that sample, but don't worry, I did. In this case, I didn't do it. But I was looking at the critical parameters. I chose the t-test. I formulated a null hypothesis. I calculated the t, and then I looked at my alpha being 0.05, so I figured out what my critical value was, and I did comparison of the critical value with the t statistic, and I decided I was either going to reject or accept the null hypothesis. In this case, I rejected it. Now realize I didn't say I reject within that value, that confidence interval. I'm sorry, I was trying to think of that. All right, proportions. Well, proportions are pretty straightforward too. So in the case of proportions, and the proportions are shown from looking at the types of problems that you're solving. But we're looking at population proportions, and this is where you've actually got a population. You're going to take a sample from that proportion, from that sample, and make some sort of claim about that, and then do this. It's easier to see in the sample. Comparing groups is a biggie, but in this case, we're going to compare the z statistic, and let's just do it. All right, here's a good sample. A political poll. You don't have to do a political poll, but this one I had to do. I am going to claim, okay, there you go. That should tell you a little something about the null hypothesis. I'm going to claim that 50% of voters support this candidate. And I've got great evidence, by the way. I sampled 500 voters with 260 of those 500 voters supporting the candidate. I want to see if this is, I want to see this at alpha equals 0.05. So my null hypothesis Okay. What I don't believe is 50% of the voters support a candidate. You need to prove this. Null hypothesis. I didn't even put it in here. So I calculate the Z. I get 0.89. Plug and chug. In this case, it really is plug and chug. Oh, there is one thing that I have to do, though, before I do that. You have to actually figure out, you've got the sample and you've got the claim. Well, the sample is 260 of 500, which is 0.52. So the probability based on the value of percentage based on the 260 and the 500 that you can compare against the 50 is 0.52 to 5. So that's a fairly low number, 0.02 difference. Plug and chug, however, and pretty big size sample size. So maybe, of course, the sample size has an effect also. But my Z comes out to 0.89. And I can just right off the bat say, well, 1.96 is going to be the critical value. And we're not going to reject the null hypothesis. There is not enough evidence that the true proportion actually is different from 50%. Might be expected because our sample was 52, and you say, well, it came out 52, it's pretty darn close. But you got to prove it. Again, so in this case, well, that's nice. There's insufficient evidence that the true proportion differs from 50%. The 52 was so, oh, wait. We failed to reject the null hypothesis. All right. Did you catch that? I think I said it right every single time. I'm going back into my memory. I mean, I've got it. I was looking at the numbers and knowing we failed to reject. Chi-squared. Here's the biggie. I am going to do some visualizations of the chi-squared. The proportions looks a lot like the other ones that you did. What are we comparing? We're comparing population variances. Why? Because it's important. The formula, the chi-squared formula, chi-squared equals n-1, s squared over sigma squared. Basically, you're looking at the differences in the variances and the n-1. It's a pretty easy equation to do. And you've got the null hypothesis of the comparison of variances. Very much, and the typical thing that you got to do, it's an independent, normally distributed population. But let's go straight to an example because this really does demonstrate it. This is also going to demonstrate why it is important. Quality control engineer wants to verify if the variability in a manufacturing process meets specifications with a maximum variance of 4. Oh, right there, maximum variance of 4. My null hypothesis is set. Yeah. Null hypothesis. Okay, we know, so right there, sigma squared is less than or equal to 4. You got 25 parts that has sample variance of 5.2. All right, well, we got enough numbers that we can actually calculate the chi-squared. Our alternate hypothesis is that it's actually the sigma squared is greater than, exceeds the specification. Okay, so the critical value, let's see, we got alpha equals 0.05, 24 degree of freedom is 24. So you can look that up, gives you 36.42. The chi-squared comes out to 31.2. 31.2 is less than 36.42. We failed to reject the null hypothesis. We failed to reject it. Doesn't mean we accept it. You can think that way. You can think we accept it. Just whenever you see the word accept, just say we failed to reject. So it is within specification. And what does that look like when you actually plot it up? Because I did create a visualization of this for you. It looks like this. There's your distribution right there with the probability density and the chi-squared values. And you can see, look, this one, which is our test statistic, is inside of the critical range, which would be anything that's to the left of that yellow line. And it's not on the right side, which is the rejection range. There you go. Pretty straightforward stuff. You use it a lot. You use it in quality control, consistency of production processes. A biggie is in scientific measurements, where you actually have to verify the validity of the instruments as part of the validity of the measurement of the actual values that you get back. And another fun one, which is financial volatility, because guess what? With financial volatility, you've also got variances that you work with, which means you can do chi-squared tests. However, they don't work real well with small samples, and they don't work real well with skewed distributions. So keep your eye out for those. You know, left skewed, right skewed, they just don't work well. Doesn't mean they don't work at all, because they're still going to be calculable. They just don't give you good results. And there actually are other ways. There are ways of actually testing the goodness of fit to see if they actually fit there. But there's other ones. There's other tests for those situations. All right, now, here's another big practicality of being in the engineering discipline and trying to do this. Figuring out the right sample size. Because we just gave you n on all those problems, but n is oftentimes what you actually want. So, what do? Well, you kind of want to know if you're within the correct precision or in the correct confidence interval, and you're looking at, well, what is the worst effect? How far off can I be from the actual value that I want something to be? And now I need to test to see if that is specifically the case. But if you get a test that's inconclusive, and what I mean when I'm saying the word inconclusive, I'm not saying that you don't draw a conclusion. It just means that you might have a situation where you want to accept the null hypothesis, but you can't accept the null hypothesis. But you might accept the null hypothesis if you had a bigger sample. Because as you noticed, in a lot of the cases that we just did as examples, where you're saying, oh, well, it's greater, this number is greater than this one, this is what we're wanting to have happen, that you actually have an improvement in test scores, but you don't have a big enough sample to prove it within the confidence you need to prove it. So what do you need? You need a bigger test size. So you can calculate required sample sizes if you if you say, oh, the number comes out to be 78, or the sample, where we want it to be above 70, we want to prove that it's 75 or higher, and we're getting 78, but you only measured one person, degree of freedom is 0. Yeah, that is not valid. Well, you measured 2 and they had an average of 78. You're still not going to be able, at some point though, if the average continues to be 78 for your sample, when you get the huge sizes, you're going to reach a point where, guess what? It does. It does prove what you're trying to prove. But, and this is a big one, it costs more money to do more samples. Now, another one is the statistical power. And statistical power is defined, the definition, probability of correctly rejecting a false null hypothesis. Okay? Correct, and I'm just going to go with that. Correctly rejecting a false null hypothesis. Now, the importance of power calculations, because this is just going to be a calculation that you're going to do, is knowing what the parameters are and what effect they have. If you got bigger samples, you increase power. If you're looking for a bigger effect, they're easier to see. If you are looking for things to be more tight or stringent, okay, you reduce power. Looser, you increase power. Okay, variability, low variability, low variability increases power. So you put those together, and you've got a calculation called power. Okay, it's just a calculation. And you're going to need to know it, because at some point you're going to be asked to calculate it. So like an example, to detect a difference of 0.5 standard deviations with an 80% power at alpha equals 0.5 in a two-tailed test, you would need, if you can calculate this, you would need approximately 64 samples per group. If you want to go from 80 to 90, it jumps up to 86 samples per group. So what you could say is that at a specific power, how many samples do you need to detect it? That's, of course, with a known standard deviation and a known alpha and a known test, in this case being two-tailed. What I mean by test is, two-tailed or one-tailed. Okay. And why do you use this? Well, you need to collect enough samples to prove what you're trying to prove. So let's suppose you're a researcher and you're designing something and you're going to do some clinical trials. And you go out and you run all your clinical trials and you're trying to prove something, but you didn't make enough of them. Well, if you didn't take enough, you're back where you started from. You can't prove it within the acceptable standard deviation, or within the acceptable alpha. Okay. You do this, and this is the same thing as doing it in materials. It's the same thing as doing it in environmentals. They're all the same thing. Okay, in the case of materials, it's usually looking at failure. You want to prove that a part won't fail, but it's the same thing. So we're going to do a lot more with hypothesis testing. I really hope I did not just flood you with so much information in here, that there's enough that you can kind of get it. But here's how you do it. You state the hypothesis, straightforward. You can't get away without looking at what you're actually doing. All of the problems aren't just a series of numbers that you plug into equations. There's a context. You've got to look at the assumptions. Okay, is the data normal? There's things that you got to look for, and then once you get to the reporting of the results, and this is why people have a hard time reading statistical reports, you might include the test statistics, the degree of freedom, the p-value, the confidence that you're using, and then what you're actually saying. Failure to reject null hypothesis. Those are again, that always bugs people when I'm trying to report. When I actually am talking to just normal people, I say, yeah, the null hypothesis looks pretty damn good. You're not going to do that with scientists. You're going to say, well, I failed to reject it. That's how it works. Sorry. So you kind of got enough now that you can do some actual hypothesis testing. We're into the real stuff. This is the stats. So we're looking forward to having a good time with this. And guess what? There's a whole lot of scenarios that we just started looking at. And I'm going to give you this, and I'm going to end up right here. This is used a lot. You see it now. Now that you're an expert, go out and read some scientific reports with reported statistical, and then now you'll look at it and go, oh, I know what that means. So thanks, and signing off. And I hope I didn't confuse anybody. I tried to do my best to get you guys to understand it. Thank you much. On out.